We have already seen wrapper methods, which are the first type of feature selection methods, multivariate feature selection methods, and we're going to move on to the second type of multivariate selection methods, which are embedded methods. So embedded methods basically complete the feature selection during the training of the machine learning model. So as the machine learning model is trained, the importance of the features is learned. So the good thing about embedded methods is that similarly to wrapper methods, they consider the interaction between the features, okay? And so they've generally been shown to be more accurate than filter methods. However, it's important to acknowledge that the feature selection for embedded methods uh, is very dependent on the machine learning method. And so if we change that method, chances are that the subset of features selected might differ. So how do embedded methods work? So these methods, as I've already said, they train a machine learning model, okay? And then basically in that training, they generally set aside a small validation set in which they use to understand what's the importance of the features, okay? And so, they train the model and use that validation set to identify how important different features are with that model that has been trained. Okay, but that happens all as we are generally training the model. There's no testing set involved, right? And so the method itself, as it's training, is identifying the features that are non-important and it's removing them from the development of the model. We're going to see two types of embedded feature selection methods that we are already very familiar with. Okay, so this is just going to be a basically remembering what we have already seen in some of the past classes and understand how that's actually performing a feature selection. So it's, covering again concepts that we know, but through a feature selection lens. And so two types of embedded feature selection are regularization, L1 regularization, and tree-based feature importance. So as you remember, L1 regularization, what it did, it's basically within a linear regression, it reduces some of the coefficients for some of the features to zero, and what that literally means is that those features are going to be removed and they're not going to be contributing to the final prediction. And so that by itself, L1 regularization is basically eliminating features that are not important, and that elimination is being made during the training itself. And then tree-based embedded methods, the way these work is that, we know that when we are building trees, like for example, random forests, there's also a way for us to understand the importance of the features, right? If you remember in the random forest class, we actually saw how to compute feature importance using an out-of-back data set, right? And so basically that feature importance is telling us which variables are more important in making accurate predictions, and then we can use those variables to basically build a stronger model. And remember as well from the random forest class that decision trees also provide us with that feature important measure either as a change in purity or in entropy or information gain, but also it can be measured as a change in accuracy. And so how would that work? If we are talking about, embedded methods for decision trees, basically what we can do is for, each feature as we keep on building the trees, we can actually understand what's the information gain for all those features. And we can compute an average information gain for the tree or across the set of trips for each of the features. And then that would allow us to rank the features. We could select the top n features given a certain threshold, and then we could basically with those features retrain the model. And again, that the implementation for that embedded method might differ across different R packages, so make sure that you check that. But it's basically just the implementation of a tree that identifies important features and then retrains the tree only with those important features. And similarly for random forest, I mean, we already saw that during the training of random forest, we can actually compute the feature importance by using an out-of-bag data set. And remember that, for each feature, we shuffled the values, we took all the points down the tree and basically computed the information gain, right? And so, we can do that, identify what's the feature importance, and then select the top n features given a certain threshold, and we can retrain the model only with those top n features. And that would basically be, a way of doing feature selection and obtaining the best model or the most accurate model.